Hi, Stu Schwartz from MasterMathMentor.com. This is video AB42. The topic is Other Growth and Decay Models, and it covers the AB manual, pages 237 and 238. In the last chapter, we showed that the statement, the rate of change of P is directly proportional to P, translates to the differential equation dP dt equals Kp. Solving this by separation of variables gave P equals C e to the kt, or P equals P0 e to the kt, modeling exponential growth or decay. It was recommended that you memorize this because the situation shows up a great deal, and it saves you the steps of solving it every time. However, if the statement, the rate of change of P is directly proportional to P, is changed or even tweaked, the solutions can be very different, some not even modeling exponential growth. It is not recommended that you memorize these situations, and when they do occur, simply set up the differential equation and solve as shown. 1a reads, the rate of change of P is directly proportional to P minus n, where n is a constant. The differential equation is dP dt equals K times the quantity P minus n. Separating, we get dP over P minus n is equal to K dt, and since we are separated, we can integrate both sides. We get the natural log of the absolute value of P minus n is equal to kt plus c, and therefore P minus n is equal to e to the kt plus c, which translates to P equals c e to the kt plus n. So this situation is still exponential growth, and n takes the curve and raises it vertically a certain distance. B reads, the rate of change of P is directly proportional to n minus P, where n is a constant. So our differential equation is dP dt equals K, quantity n minus P. And to separate, we will write this as dP over P minus n is equal to negative K dt, because it is a little bit easier to integrate dP over P minus n. This gives us the natural log of the absolute value of P minus n is equal to negative Kt plus c, or P minus n is equal to e to the negative Kt plus c. And our final statement is P is equal to C e to the negative Kt plus n. So this signals exponential decay, and the n will again raise the curve vertically. C reads, the rate of change of P is directly proportional to the square root of P. Our differential equation is dP dt is equal to K square root of P. And separating, we get dP over the square root of P is equal to K dt. Integrating both sides, we get 2 square root of P is equal to Kt plus c. Solving for P, we get the square root of P is equal to Kt over 2 plus c, realizing that c over 2 is simply c. And therefore, we square both sides, getting P is equal to the quantity Kt over 2 plus C quantity squared. So in this case, the rate of change of P is directly proportional to the square root of P, gives quadratic growth. D reads, the rate of change of P is inversely proportional to P. That means that dP dt is equal to K over P. And we can then write that as P dP equals K dt, and integrate both sides, getting p squared over 2 is equal to kt plus c. Solving for p, we multiply both sides by 2, getting p squared equals 2kt plus c, realizing that 2c is still c, and therefore p is equal to the square root of 2kt plus c. So the statement, the rate of change of p is inversely proportional to p, gives growth based upon a square root. You might wonder why in C, when we divided k by 2, we didn't get k, and in D, when we multiplied by k by 2, we didn't get k. That is different than what happened with C. The reason is that in many of these problems, k may be given to you. It might be called the constant of proportionality. And therefore, if we divide by 2 or multiply by 2, we change it. So with k, we simply do the regular arithmetic, but with the c, we do not. And we just say that 2c is equal to c, and c divided by 2 is still c. Number 2 reads, suppose you fill a tall cylindrical can with water and punch out a hole near the bottom. The water leaks out quickly at first, then more slowly as the depth of the water decreases. The rate at which the height of the water in the can changes is directly proportional to the square root of its height. At t equals 0, the height is 20 centimeters and is falling at the rate of 5 centimeters per second. The water comes out quickly at first because the can is nearly full and the entire weight of the water puts pressure for the water to leak out very quickly. But as the level of the water goes down, the pressure is not as great, which means that the water will leak out less quickly. And when the water reaches about the level of the hole, there's almost no pressure at all, so it just sort of dribbles out. We are first asked to write and then solve the differential equation that describes this situation. Since the rate at which the height of the water is changing is not directly proportional to its height, but the square root of its height, we need to go through the following steps. We know that dh dt will equal k times the square root of h. When t equals 0, dh dt equals negative 5, and we know that at that point h is equal to 20. So negative 5 is equal to k square root of 20, and therefore k is negative square root of 5 over 2. Therefore, dh dt is equal to negative square root of 5 over 2 square root of h. This is a separable differential equation, and we get that the integral of h to the negative 1/2 dh is equal to negative square root of 5 over 2 dt. We can now integrate, getting 2 square root of h is equal to negative square root of 5 over 2t plus c. And now we would like to solve this for h, so we'll divide both sides by 2, getting the square root of h is equal to negative square root of 5 over 4t plus c. And we squared both sides to get h is equal to the quantity c minus the square root of 5 over 4t, quantity squared. Next, we have to solve for c. We know that at t equals 0, h is equal to 20, and therefore 20 is equal to c squared, and therefore c is equal to the square root of 20, or 2 square root of 5. So we can now write our statement for h is equal to quantity 2 square root of 5 minus the square root of 5 over 4t, quantity squared. And when we expand that expression, we get h is equal to 20 minus 5t plus 5/16 t squared. We could factor out the 5/16 and write that as h is equal to 5/16 times the quantity t squared minus 16t plus 64, and therefore h is equal to 5/16 times the quantity t minus 8 quantity squared. Part B asks, when is the can empty? And this is easy. We just set h equal to 0. 5/16 quantity t minus 8 quantity squared is equal to 0, and therefore t is equal to 8 seconds. This again is assuming that the hole is as close to the bottom as physically possible. Also shown to the left is the slope field for dh dt equals negative square root of 5 over 2 square root of h. And the solution, h equals 5/16 quantity t minus 8 quantity squared. Number 3 reads, a curve passes through the point 0, 10 and has the property that the slope of the curve at every point P is twice the y-coordinate of P. We want to find the equation of the curve. This problem doesn't specifically use the magic words that the rate of change of P is proportional to the value of P. But in reality, it is saying that the rate of change is the slope, and twice the y-coordinate is simply multiplying by a constant. But if you didn't realize this, we can still do the problem. dy dx is equal to 2y, and separating we get dy over y is equal to 2 dx. Now that we're separated, we can integrate both sides, getting the natural log of the absolute value of y is equal to 2x plus c. Or y is equal to c e to the 2x. Utilizing the fact that when x is equal to 0, y is equal to 10, that gives us c is equal to 10. And therefore our equation is y is equal to 10e to the 2x. The slope field for the differential equation in red and the particular solution in blue is a good verification of our answer. As the y-coordinate gets larger, the slope gets twice as large. And that is true whether y is positive or y is negative. Problem number 4 is the type of problem that usually shows up on a free response question on the AP exam. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and the outside air. Suppose that a pork roast is taken from the oven when its internal temperature has reached 160 degrees and is placed on a table where the temperature is 75 degrees. Let R be the temperature of the roast T minutes after it has been taken from the oven. We first want to create and then find the general solution to the differential equation. Since R is the temperature of the roast and it is cooling at the rate that is proportional to the difference between the object and the outside air, dr dt will equal k times the quantity R minus 75. We can separate this and write this as the integral of dr over R minus 75 is equal to k dt. Integrating, we get the natural log of the absolute value of R minus 75 is equal to kt plus c. R minus 75 is equal to c e to the kt, and R is equal to 75 plus c e to the kt. This is a general solution, but we still have two constants we need to find in order to get the particular solution. First, we need to get the value of c. We utilize the fact that when t equals 0, R is equal to 160. So 160 equals 75 plus C, making C equal to 85. And therefore, our general solution is R is equal to 75 plus 85 e to the kt. To actually find a particular solution, we need to find K, and we need one extra piece of information. Question B gives it. If the temp of the roast is 120 degrees after 30 minutes, what is the temperature after 45 minutes? So we use the fact that when T equals 30, R is equal to 120. Plugging in, we get 120 equals 75 plus 85 e to the 30k, and 45 is equal to 85 e to the 30k. Solving for k, we get k is equal to the natural log of 45 over 85, all divided by 30. And that is equal to negative 0.0212. If you are going to use this for calculations, I suggest that you store the value of k in memory on your calculator. We then find the value of r of 45, and we get 107.742 degrees. We also want to find how long it will take for the roast to cool to 90 degrees. So we set 90 equal to 75 plus 85 e to the kt. Remember, we know the value of k because it has been stored. So therefore, 15 is equal to 85 e to the kt, and t is equal to the natural log of 15 divided by 85, all divided by k. And when we do the calculation, we get 81.822 minutes. Shown is the slope field for our differential equation and the particular solution in blue. R equals 75 plus 85 e to the kt, where k has been calculated as shown. The two given points, 0, 160, and 30, 120, are in red, and the 2 points we found, 45, 107.7, and 81.890, are in blue. The line y equals 75, shown dashed in green, is a horizontal asymptote to the curve, as the limit as t approaches infinity of r of t is equal to 75. Note that the cooling takes a while. The roast does cool quickly at first, so you don't want to wait too long to eat it. But after 2 hours, the cooling has slowed considerably, and the temperature is still about 5 degrees above room temperature. Also note that if the pork roast was taken out of the freezer when it was frozen solid, it would also adhere to Newton's law of cooling, even though in this case it's warming up. Eventually, the pork roast will reach room temperature. Number 5 reads, fish are being introduced into a man-made lake. The change in the rate of fish, F, is directly proportional to 900 minus F, where T is measured in years. When T equals 0, there are 400 fish in the lake, and 3 years later, there are 600 fish in the lake. Our first challenge is to write and solve the differential equation that describes this situation. Our differential equation is df dt is equal to k times the quantity 900 minus f. We will write that, multiplying both sides by -1, to get the integral of df over f minus 900 is equal to negative k dt. Integrating, we get the natural log of the absolute value of f minus 900 is equal to negative kt plus c, and therefore f minus 900 is equal to c e to the negative kt, and therefore f is equal to 900 plus c e to the negative kt. There are two challenges here. First, we have to find c, and then we have to find k. We have 2 points to do this with. When t equals 0, f is equal to 400. So 400 equals 900 plus c. C is equal to negative 500. And therefore, f is equal to 900 minus 500 e to the negative kt. When t equals 3, f equals 600. So 600 equals 900 minus 500 e to the negative 3k. And therefore k is equal to the natural log of 3/5 divided by negative 3. And that is equal to 0.1703. Again, it's recommended that if you're going to be using this for calculations, as we'll have to store this value on your calculator. So f is equal to 900 minus 500 e to the negative 0.1703 t. B asked to find the fish population in another 3 years. So we'd like to find the value of f at 6. Plugging in, we get approximately 720 fish. Finally, in C, we'd like to find the limit as t approaches infinity of f of t, and that is equal to 900. So as time goes on, the fish population in the lake should level off to 900 fish. Finally, here is a graph of the slope field, the differential equation, and the particular solution. Note that it goes through 2 points in red, 0, 400, and 3, 600. And the point that we found, 6, 720 in blue. The curve is asymptotic to the line y is equal to 900. Also note that if the lake were overstocked with fish and there were too many in there, that the model still works, that the number of fish would go down, presumably because there wouldn't be enough food in the lake, and again will become asymptotic to 900. That's it for the AB course. There are other videos in this series covering the non-essential areas of AB calculus, and these, while not explicitly covered on the AP test, will enhance your knowledge. There is a huge amount of review material on the MasterMathMentor.com website, specifically for the AP exam. Most of it is free, and the solutions are not expensive if you choose to purchase them. I hope you have benefited from these videos and they enhanced your learning if you use them in the dark days of COVID. If you take BC Calculus, remember that that course has videos for all topics as well.